The dot diagrams clearly show what is called the octet rule. Metals such as sodium, they lose their electron to a nonmetal such as chlorine. And when this happens, then chlorine has 8 and the sodium would drop down to the next energy level. So it would have 8 also, dropping down to the 2s2, 2p6 row. The octet rule basically says that atoms gain, lose, or share electrons to achieve 8 valence electrons, just like a noble gas. They don't become a noble gas. They will still belong to their same family. They'll still be metals. They'll still be nonmetals, but they are copying that lower level stable electron configuration. And the octet rule always has to do with the S and P sublevels. S has 2, P has 6, just like it says right here. That's where the 8 comes from. Down here at the bottom, we have water formed, and how this happens is the oxygen and the two hydrogens, they share. And so you can count that oxygen has 8 valence electrons and hydrogen has 2. Hydrogen's just too small to have 8. So by sharing an electron with oxygen, it has 2 valence electrons, so it's copying its nearest neighbor, helium. So next, let's talk about ionic bonds. In ionic bonding, metals are bonded to nonmetals, and there's an electron transfer. When those electrons transfer, you end up with a positive cation and a negative anion. And what holds it together is that electrostatic force, or opposites attract. Here I have an equation that shows sodium solid reacting with chlorine gas to get sodium chloride solid. And this is the amount of energy that is released. When I have a negative sign right here, this shows that this is an exothermic reaction. And what that means is that the energy is exiting from the reaction, and so it's going to feel warm. The process of reacting, sodium loses an electron to chlorine, and then this makes them both have an octet. And here's a crystal structure down here. You can see that it's a repeating pattern of positive minus over and over and over, and these end up being very, very large crystals. Here's a chart of exothermic and endothermic. Again, you can see here in exothermic that the energy exits. That's how we remember it, energy exits. So we have a starting point right here with our reactants and an ending point as far as energy goes. And so you can see that the energy level drops. And where did that energy go? Well, it exits in the form of heat. Endothermic, that is the opposite. So the energy enters. So that's how I remember it. So we have enters, endothermic. We have our reactants starting out low. Our products start out with a higher amount of energy. Well, where did this quantity of energy come from? Well, it enters into the reaction. If you had a beaker that contained an endothermic reaction, you put your hands around the beaker, it would feel cold. And that is because the heat from your hand would get sucked into through the beaker into the reaction. And so our brains would interpret that as, oh, heat is leaving, so this is cold. And then the opposite, which I didn't mention, this exothermic, it feels warm. And that's, again, because the heat is leaving for exothermic and the heat is being absorbed in the endothermic. Let's look at a concept called lattice energy. This will for sure be on the AP test. They ask a question on the AP test every year that relates to this concept. So when we look at an ionic compound, again, we have this repeating plus minus crystal structure that's over and over again. And what if we were to take and remove one of these cations away from the crystal, or maybe one of the anions? So what is the amount of energy would it take to pull this apart? And it is defined as the energy required to separate the solid into its gaseous ions. So there's going to be some sort of energy exchange there because we're going from a solid to a gas. But there are two things to look at when you're looking at lattice energy. The first one, and it's the most important, is the charge. So you could have a +2, a -2 crystal structure, or a +1, a -1 crystal structure. And the charge is the most important. So the higher the charges, then the higher the lattice energy. So, and this all relates to Coulomb's law. So because my charges are higher, it's going to take more energy to take it apart. Um, and that's comparing the +2 -2 to the +1 -1 crystal. The +1 -1 won't take as much because it has a lower charge. The second thing you can look at is the size of the atom. So the smaller atom, that means it's closer together. And according to Coulomb's law, if they're closer together, then you're going to have to put in more energy to take them apart. So um, again, two things to look at. First of all, charge is the most important. And then the second thing to look at is the atom size. So let's look at this problem. Arrange the following compounds in order of lattice energy. So the largest to smallest. So make sure you pay attention to what is being asked. So I'm going to first look at all these charges. So on my first compound, lithium, it's an alkali metal. It has a +1 charge. And fluorine is a halogen. It has a -1 charge. And next I have magnesium. It's an alkaline earth metal. It has a +2 oxidation number. And the oxygen in the oxygen family has a -2 oxidation number. And the last one, potassium, is also an alkali metal with a +1. And my fluorine, we already did that one. It's a halogen, a -1. And so I can go through and I can, first of all, compare the charges. So, and it looks like my largest charges are here. Again, that's the most important thing. So from largest to smallest, this one is first, okay? Just based on charge. The next thing to look at is the size. So when I look at lithium fluoride, I'm going to have a lithium atom, and it's towards the top of the periodic table. So here's lithium right here. And so I know that as I go up a family, it's going to get smaller and smaller. So lithium's going to be a pretty small atom. So again, smaller as I go up. And if I look at fluorine, so fluorine's right here, it's also towards the top. And so we're looking at two pretty small atoms here. Fluorine does get an electron from lithium, so it gets a little bit bigger than its atom, but it's still going to be quite small. Let's look at this next one, this third one, I should say. I have potassium. Potassium is a little bit further down on the periodic table, so it's just right there. And so it's going to be a little bit larger, so I'm just going to draw it. It does lose electrons, so it's a little bit, the cation is a little bit smaller than the atom, but it's still going to be bigger than that lithium. And then we're comparing it to fluorine. Okay, so there's my fluorine. So when we look and arrange it in order for size, again, the smaller it is, the harder it's going to be pulled apart. So I would next, I'm really just comparing the potassium with the lithium. And so because the lithium is smaller than the potassium, this one's going to be the second largest lattice energy, and then this one's going to be the third. So again, look at charge first. So that's how I got my number 1. And then look at size. And lithium is smaller than the potassium, so it's going to be the next largest. So here's an extension question. So which would have the highest melting point? So when you're melting something, you're taking this regular crystal arrangement and you're melting it, so it's a little bit more jumbled. So really what you're doing is you have to put in energy to satisfy that lattice energy, the energy that it would take to pull it apart. And so you would look at the one with the highest lattice energy would be the one that has the highest melting point. So it would be in the same order. So MgO would have the highest melting point because it has the highest lattice energy. Here's a chart of lattice energy so we can see how we did. And look, there's that MgO, and it has almost 4,000 kilojoules per mole to pull that apart. And then we looked at potassium fluoride, and we looked at lithium fluoride. And you can see that lithium fluoride being the smaller between the potassium and lithium, that it is a little bit more. So again, charge is most important, and the next size, and we do see that we predicted it correct. Hess's law is an energy concept, And it says that the amount of energy released or absorbed in intermediate reactions is equal to the same energy if the reaction occurred in one step. So in other words, if I was going from 1 to 3, so if I was going this way, 1 to 3, it would be the same energy as if I went from 1 to 2 and then 1 to 3 and then just added them up. So again, if the reaction is in one step or it could be in multiple steps, but the energy released or required would be the same. And this happens a lot in chemistry. Chemistry teachers, we sometimes joke that we stand in front of you and lie a little bit. And that is because the chemical reaction process is often not in one step. It might be in 6, 7, 8 steps. And that just gets really, really complicated. So chemistry teachers simplify things just so it's a little bit easier. But the energy required or released is the same. So whether it occurs in one step or in 2 steps or in 7 steps, it's going to be the same. And this is known as Hess's law. So it's a way to just simplify things. So let's take you through a chemical reaction. And this one has 5 steps, okay? The red arrows, they signify an endothermic process where we're putting energy into it, and the blue arrows represent an exothermic process. So notice that both are present, and when you look at the overall reaction, we do see that it is exothermic, that more energy is released than was required. So in other words, at the beginning, energy was put into it, but then at the end, more energy was released than was put into it. Um, this is called the Born-Haber cycle. It's used to make sodium chloride from gas ions. So let's go through this step-by-step process, starting with number 1. So first of all, we take the sodium solid and we make sodium gas. Notice that we had to put energy into doing this, so we had to heat it up. Next, we take chlorine, and we take the molecule and we split it up into its atoms, so gaseous atom. Remember, chlorine is diatomic, so that means it's connected to another atom of chlorine. And in this step, we're just separating it out, breaking that bond. And then we take and remove an electron from the sodium. So that's our third step. Our fourth step is that electron is given to the chlorine atom, and so we make a chloride ion, a gaseous chloride ion. So now that we have a gaseous sodium ion and a gaseous uh, chloride ion, then we can put them together and we get this reaction right here. Okay, and so this is basically the opposite of lattice energy. So lattice energy is going this way, where you take the solid and then you make the gaseous ions. So if I made the sodium chloride solid and it released 787 kilojoules per mole. If I were to go backwards, then to do the lattice energy going the other way, it would take that amount of energy. So it would take a positive 787 kilojoules per mole. So, and that's the answer to this. What is the lattice energy? Well, the opposite of this step. So I would take and have to put in this amount of energy.